Cover section 5.1 today, which is on area under the curve and finite sums. If I can get to my graph paper, there it is. So, if I can enlarge the screen, that would be helpful. Section 5.1, area and estimating finite sums. And again, your homework in this material is not difficult, but it is time-consuming. So kind of give yourself some time. Okay, so what are we learning here? What's the goal? The goal here is to find the area under a curve. So you're going to graph a curve, and you're looking for the area under the curve, between the curve, that says under, between the curve and the x-axis. And how do we do that? How in the world are we going to find this area? Well, later we're going to find the area using integration, but we're going to kind of warm up to it by creating rectangles under the curve and just using length times width to get the area of each rectangle to get an approximation of the area under the curve, and also kind of give a vision then of how integration will work. So in other words, if you have a curve, and we'll just do a rough draft here of a curve, I don't know, something like this. Okay, there's a curve, and your goal is to find the area under the curve. Well, suppose you want to go from the origin to a point x, and we'll call it x sub 1, and you want the area under this curve, an approximation to the area under the curve. Then if you want to find the area, you take your height at x1, and you create a rectangle, and you find the area of that rectangle. So the area of a rectangle is length times width, or maybe we should put width times height, HT, height, to kind of so that we don't get confused with what's the width and what's the length. So instead of it being length, we'll call it height. And so in this case, we would have a width of x sub 1, right? That's how wide it is. I don't know how to write this. The width is x sub 1 from 0 to x sub 1. That width is x sub 1. And your height, if this function is f of x, this height is f of x sub 1. That would be your width times your height, which would give you the area of this rectangle that we've drawn between the origin and that point on the curve. And then you can continue to do it again. Suppose this is point x sub 4 and this is point x sub 5. And so you want to find the area of the rectangle under the curve. Well, suppose I use the height from x sub 4 instead of the height from x sub 5. Then the area of that rectangle, again, is width times height. And this width, which we often refer to it as delta x, the width is delta x. In this case, your delta x would be x sub 5 minus x sub 4. And your height, if you choose the height at x sub 4 in this case, then your height is f of x sub 4. And you will have the choice, kind of, as to which height you use. You'll call it an upper sum or a lower sum. We'll discuss that with great length. So in this case, the area of the second rectangle would be the width, which is x sub 5 minus x sub 4, times the height, which is f of x sub 4 in this case. So it really is that easy. Now this second example, which we just did, again, I'm trying to put emphasis on the height that we chose. Note if we chose the height of x sub 4, your rectangle would be as I drew it. But had you chosen your height of x sub 5, then your rectangle would be above, right? See the difference in the two rectangles? One's an underestimate and one's an overestimate of the area of the curve between those two x values. If you chose f of x sub 4, that is considered the left end point version of finding the area. And if you chose the right, then it would be the right end point version of the area. And so we talk about left end point sums and right end point sums and upper and lower limits. So this one is also considered the lower sum because it's under the curve and it's a little short of the true area. If you had chosen x sub 5 for your height, you'd be upper sum, kind of a little bit of an overestimate. And we'll go into greater detail about this as we move along. But something that we need to discuss about these areas is that the accuracy of our area under the curve, our accuracy in making all these rectangles and adding them up, is dependent upon how wide you choose or how large you choose delta x to be. The goal really is to have this delta x as small as possible in order to get accuracy in the area under the curve. So FYI, accuracy is dependent upon how small we choose delta x to be. How small we choose the width of each rectangle to be. And the smaller it is, the more accurate we will come up with the area under the curve. So we'll find that out as we move into the next section, actually as we move through the chapter, how that works. Okay, so we'll play around a little bit with some examples so you can see that this is not difficult. But again, it is a little bit time consuming. It's very logical. It's very easy to understand. Again, if you understand the underlying concept of adding up the areas of the rectangles under the curve. Okay, so let's estimate the area under the curve. And the curve is y equaling x squared from, it's going to give us some endpoints, from 0 to 1. And it says use 4 rectangles. So we're going to use 4 rectangles under our curve in order to come up with this estimate of the area. Well, we're going to start off by doing the right endpoint. Okay, let's start off by using the right endpoint. Well, if I draw this curve, a rough draft of this curve, I'm going from 0 to 1. Okay, and I want 4 rectangles. Let me get on the screen. If I want 4 rectangles, how wide should each rectangle be? What should be the width? A quarter. So here at 1/4, here at 2/4, which is 1/2, here at 3/4, and there at 1. That's going to give me the 4 rectangles. Well, at 0, x squared is 0. At 1/4, it's only 1/8. Oh my. How high should I go? Okay, so 0, 0, 1/4. No, that's 1/16. It's tiny, tiny. Oh, that's lousy. Okay, at 1/2, it'll be 1/4. At 3/4, it'll be 9/16. And at 1, it'll be 1. So this is something of a, supposed to be a parabola, people. Okay, like that. Okay, so there's an estimate of the graph. Okay, so if I'm going to use the right endpoint, my area is going to be my first rectangle to the right endpoint. It's going to look like this. So my first one is my delta x. What is my delta x? Well, we can write it. Delta x, f of x sub 1, right? That's your first rectangle if f of x sub 1, or if x sub 1 is 1/4. Your second one is delta x times f of x sub 2. That's your second rectangle, which is a height of 1/2. Your third rectangle will be delta x times f of x sub 3, which is 3/4 right here. And your last one, which I'm running out of room, is delta x f of x sub 4, which is right here. There's your 4 rectangles based on using your right end point of the interval to give you the height. So you know right now we're going to be way overestimating this thing. It's going to be overkill on the area under the curve because we're going above the curve. So this is considered the upper sum. Well, this turns out to be delta x, the width of the first rectangle is 1/4, and then f of 1/4. The second one, the width of the rectangle is 1/4, and you're wanting the vertical value at an x value of 1/2. The third one, your width is still 1/4. The width of this rectangle is 1/4, and the height at 3/4. And the last one, your width of 1/4, and your height, I got too many parentheses, at 1. There's your length times width, or your width times height of every one of the 4 rectangles using the right end point of each width, or the right endpoint of each of the rectangles. So this becomes 1/4 times f of 1/4. Go to your function. 1/4 squared is 1/16. The second one is 1/4 times the height at 1/2. 1/2 squared is 1/4. Then you have 1/4 times your height at 3/4. 3/4 squared into your function. 3/4 squared is 9/16. And then f of 1 squared is 1. So this turns out to be something. Oh my. Anybody have any value for me on that? Is it like 30 over 64? This is 1 over 64. This would be 16 times 4, so this is 4 over 64. This is a 64, 9 over 64. And this would be 16 over 64, right? If I did that right, that's a miracle. I got 31 over 64.
I think it's 50. I got 50 over 64.
No, 30 over 64. Is that what I got? Okay, how can we all have such different answers? 1 plus 4 is 5 plus 9 is 14 plus 16 is 30.
I think you're right. I think it's 30 over 65. That reduces. But I just used the decimals.
Thank you. She's in agreement with me. Girls rule. What is the decimal value of this? 0.88. Okay, there you go. Approximately that. Now this is considered the upper sum. Now why would it be called the upper sum? This is really simple terms.
Overestimating.
There you go. We're overestimating. All of our vertical values are high. Okay, we're up above the curve, so we have overestimated. Okay, it's pretty good. I mean, it's better than not just guessing, right? It's better than just pulling numbers out of the top of our head. But that's the area of what's considered the upper sum using the right endpoints. Now, suppose we wanted to do the same thing, but we want to use the left endpoint. Now, this would be a lower sum, right? Because we're going to be a little lower. So let me change the pen color. See if this can become visible. Okay. In this case, I'm going to use the left side. So when I do the area, okay, it's going to be on the first one, delta x, which is 1/4, times not f of 1/4, but f of what? F at 0. So it's the height here. Like that's going to be like no rectangle, right?
0.
There you go. That's right. Then the next one, the width is 1/4, but f of 1/4, which is right here. The height, it's the pink one. That's the left end point. Your x value is 1/4 on the left end point. Then the third rectangle is delta x, f of 1/2, which is a height up here, going over. And then your next one is delta x times f of 3/4, which is your height at 3/4 coming over. So these rectangles are staying under the curve, so it's an underestimate. This is the lower estimate, the lower sum. Delta x continues to be 1/4, and f of 0 is 0, so that one's a 0 out situation. Delta x is 1/4, and f of 1/4 is 1/16. Delta x is 1/4, and f of 1/2 is 1/4. And delta x is 1/4, and f of 3/4 is 9/16. So this turns out to equal 0 plus 1 over 64 plus 1 over 16 plus 9 over 64, which equals 0 plus 1 over 64 plus 4 over 64 plus 9 over 64, which is 14 over 64, which is 7 over 32, which is what in my decimal? Let me get on the screen. What is my decimal value? Okay. So the true area is between 0.2188 and 0.4688. So So about 0.3 something, okay, would be the true area under that curve. Now this again is considered the lower sum because the true area should be more than that. Okay. Now, when we write the area, this line right here, okay, this line right here where I have delta x, f of 0, delta x, f of 1/4, delta x, could this have been rewritten as delta x times f of 0 plus f of 1/4, right? Right. So since we're choosing delta x to be consistently at 1/4, you can algebraically write it delta x and then just put the sum of all this, like factoring out the delta x. So you can pull the delta x out front and then compute all those sums. Okay.
Is it always the same, or can you do differently?
Everything we will do, the delta x will be the same. Riemann, when we go into Riemann, he chooses not to do it the same, so he has good accuracy. But what we're going to do is keep the delta x the same because it would be ugly if we did not. Yes, you can work really, really hard. Okay, so that's pretty neat that you can get a right endpoint area, a left endpoint area. And you know, this is an increasing function, but if the function was decreasing, the left endpoints would be an upper limit and the right would be the lower. So it depends on the shape of the graph according to which one's an upper and which one's a lower to get those heights such that you're either overestimating or underestimating. Okay, I'm going to open the textbook and show you some diagrams which are kind of nice, help you have a little bit of a better vision of this. I think I'm going to page 248 just to look for a minute of what's here. They have nice colored diagrams. You can see in these figures in the left column, you can see here this is the lower sum where all of these rectangles are under the curve, and you can see this is the upper sum where your rectangles are above the curve. So looking again, if you look at one of these rectangles, is the height of each rectangle determined by the left endpoint or the right endpoint of the interval?
That one's the left end.
I disagree. I'm going to drop this book on the floor. Look at this one right here. There you go. Look at this rectangle. Is the height of this rectangle computed using the right endpoint or the left endpoint of the rectangle?
Right.
There you go. So this one is the right endpoint sum because the height was based on the right side of the rectangle. Okay? This is a decreasing function. So in this picture, when they find the area of these rectangles, the width is consistent, but the height of each rectangle, is it determined by the left endpoint of each rectangle or the right?
That one's the left.
Okay, pick a rectangle. Pick one. Is the height of this thing determined by the left endpoint or the right endpoint? The left endpoint, right? The height is determined by the left side of the rectangle. Okay, and as you do your homework and you're drawing your own rectangles, that'll solidify. Okay, it'll make a little more sense because you'll be more comfortable. And of course, the more rectangles you choose, the more accuracy you're going to get. Okay, or meaning the smaller the width of the rectangle, the more rectangles there will be under the curve, and therefore you will get more and more accuracy. Okay, so let's do another example. It's kind of fun. If I get off the screen, be certain to say something. Okay, so let's estimate the area under the curve. And here's your curve, f of x equaling 25 minus x squared. So with a negative x squared, this is a concave down parabola. And you want to find the area of the curve over the intervals from 0 to 5. Okay, and let's use 5 rectangles. And usually they'll tell you how many rectangles to use. Use 5 rectangles. Okay, so all that's left is determine, do we want to use the right endpoints or the left endpoints? So let's go in and let's use the right endpoints. Well, since this is a concave down, using the right endpoint, I think is going to be a lower sum, isn't that right? Yeah, it'll be under the curve. So we have to kind of look at it. I tend to want to graph it briefly because it makes it so much easier to visualize it. So if I graph this concave down parabola between 0 and 5, 1, 2, 3, 4, 5. Oh my gosh, okay. So this will be 1, 2, 3, 4, 5. So when I'm going to divide it into 5 rectangles, which makes the width 1 on each one of these rectangles. At 0, the height is 25. 5, 10, 15, 20, 25. I'm going to go by 5. So here's the first one. At 1, 25 minus 1 squared is a height of 24. It barely dropped. Okay, like right here. Okay, at 2, 25 minus 2 squared is 25 minus 4, which is 21, which is about right there. Then at 3, 25 minus 3 squared is 25 minus 9, which is 16. At 4, 25 minus 4 squared is 25 minus 16, which is a height of 9. And then at 5, 25 minus 5 squared is 0. So here it is, our parabola concave down. Like so. So if we use the right endpoints, okay, my area, let's see if I can fit this, I have to come down. My area is going to be my delta x, which is my width, times my f of x. If it's a right endpoint, do I start with f of x? Well, delta x. F of x of 1, and then delta x, f of x sub 2, and then delta x, f of x sub 3, delta x, f of x sub 4, and then delta x, f of x sub 5. Okay, so my delta x every time is what? Is 1. So I'm going to pull it, I'm going to go ahead, I think this makes it a little easier. Plus, you need to get comfortable with this notation. Okay, and your delta x is going to be 1. Okay, so my f of x sub 1, is that f of 0 or f of 1? Okay, so is my height going to be determined by an x value of 0 on my first rectangle, or a height at an x value of 1? At 1. So this is f of x 1. This will be f of 2, this will be f of 3, this will be f of 4, and this will be f of 5 because I'm using the right endpoints to determine the estimate of the area because that's what the question said to do. So this is 1 times f of 1, this is your height. When you draw it, here is your height. You're just a little bit under the curve. So your height there, f of 1, is 25 minus 1 squared, which is 25 minus 1, which is 24. Your height at 2, right here, is 25 minus 4, which is 21. Your height at 3 is 25 minus 9, which is 16. And your height at 4 is 25 minus 4 squared, 25 minus 16, which is 9. And your height at 5 is 0. So it doesn't contribute a whole lot to the area of the rectangles under the curve. So this turns out to equal 1 times 24 plus 21 is 45. 45 plus 16. 45 plus 16 is 61. 61 plus 9 is 70. Did I do that right? So the area here is 70, and this is considered your lower sum because you are under the curve. This is a decreasing function. So your error is these little half sunbursts, you could call them. This is your area. These little, that's a big, that's a bad one, okay? But your area your error is in these little regions, okay, above the rectangles but still under the curve. Now another way, this was the area using the right endpoint. Now another way of doing this simple, is to find the area. Instead of using the right endpoint or the left endpoint, what if we want to use the midpoint of the interval? Wouldn't that be pretty darn good accuracy to be at the midpoint of each rectangle? Okay, well think about it. If your midpoint of the first region is right here, then your height is right here, and so you're going to be under it on this side but a little above it on that side, right? Which means your error under and your error above is very close. So here is your midpoint height. See that? So here on this one, your midpoint height is right here. So you're under the curve on the left, but above the curve almost the same amount on the right. Are y'all visualizing that? Where's my pencil? Here's your under the curve estimate. Here's your above the curve. So those are almost perfect reflections of each other for error under and error above with the pink rectangle. So your midpoint, let me try one more. If I do the midpoint here, your height is up here. So your rectangle would look like this. Now, maybe this time you can see. Okay, your error is here under the curve, short. You're short this much that I'm shading, but you're above this much. So the amounts you fall short and the amounts you overestimate are very similar. All right, it's kind of hard to get a beautiful graph. Okay, but when you do this one, your area for the midpoint, okay, is your delta x, which is still going to be 1. The width of these rectangles, even though I'm using the height at the midpoint, the width of this rectangle is still 1. Okay, so everything is 1. But in here, these x values are going to be different. So here we go. Your delta x is 1. Your f of x sub 1 is f. Your x is not 0 and your x is not 1. Your x value at that midpoint is 1/2. What is your x value at the midpoint of the second rectangle? 3/2. And the third rectangle is 5/2. 7/2, and 9/2. So these are not as, these aren't hard to evaluate, but you're playing with fractions a little bit, which just takes a little more time. So f at 1/2 is 25 minus a fourth, which is what? 24 3/4, which is what? 24.75. We'll just do that. Let's make it easy, okay? Okay, f at 3/2 is 25 minus 9/4, which is 25 minus 2.5, which is 22.5. Is that right? Okay. F at 5/2 is 25 minus 25/4, which is 75/4. I might just have to write that. F of 7/4 is 25 minus 49/4, which is 51/4, right? And 9/2 is 81/4, which would be 19/4. Okay, what in the world does that come out to be? About 83.75, does that sound right? Okay, so it's not difficult here, but you start using a trig function, your midpoints turn out to be kind of ugly, you still will get pretty good accuracy on the midpoint. Just don't rush. You'll be really frustrated. And this textbook does not provide nice diagrams. It doesn't give you a good visual. Okay, so there's your midpoint. You might want to put an asterisk by that. I think that you can do that without any issue. But that is using the midpoint. Instead of using the left end point or the right end point, using the midpoint is a pretty good estimate of coming up with the area under the curve, because your overestimating error is about the same as your underestimating error. So that works nicely. Okay, now another thing that's so nice about this area under the curve is when you start talking about distance. Okay, when you start talking about distance or distance traveled, when you start talking about distance, distance happens to be the area under the velocity curve. Okay, so if you have a function representing the velocity of a moving object, then the area under velocity will tell you the distance that an object is moving. Okay, so let me pull up the textbook because it does a pretty good job of trying to explain this. So on page 249, and it says, it's just kind of neat the way it's well written here. It says, I have it all underlined. When we don't know the antiderivative for a velocity function, sometimes taking the antiderivative is not algebraically an easy thing to make happen. So if we don't know the antiderivative for a velocity function, we can apply the same principle of approximating the distance traveled, because the antiderivative of velocity is distance, by using finite sums, meaning using sums of the areas of rectangles, a very specific number of them, in a way similar to finding the estimates under the area under a curve. So if you have a velocity function that you can't take the antiderivative of, you can always go to using the area of the rectangles under the curve to come up with the distance the object has traveled. So the antiderivative of velocity is distance. So take, for instance, let's see if I have enough room here. I might not. I'm going to have to change paper. Here I am trying to conserve my pieces of paper. So here, I can do some of it on here. So here's a table. Okay, and it's going to tell me time, and it's going to tell me velocity of a moving object. So at time 0, say your object is already moving at, 30 miles per hour. 12 seconds later, your object has slowed down to 28 miles per hour. 24 seconds in, you're at 25 miles per hour. 36 seconds in, you're at 22 miles per hour. 48 seconds, you're at 24 miles per hour. And then a minute, you're at 27 miles per hour. Now, if they want to know the distance that this object traveled, and they say use 5 rectangles under this curve, whatever the curve looks like, what is delta t? What is the change in time? Is it consistent, number one? What is it? It's 12. Okay? So fortunately, they gave us data in which we had 12 seconds between every time they caught the velocity of the moving object. So if you want to graph this, even though you don't even know the equation of the velocity curve, you can go 12, 24, 36, 48, and 60. At time 0, you're at a height of 30. How do I do this? 10, 20, 30. You're at a height of 30. At 12 seconds, you're at a height 28. 24 seconds, you're at a height of 25. At 36 seconds, you're at a height of 22. At 48, you're back up at a height of 24. And at 60, you're back up at 27. So this is not a parabola, or, this is just a gentle curve. But you can find the distance this object traveled. This is your velocity. Your vertical is your velocity, and your horizontal is time. Now, the area under this curve, And what does it want me to use? It wants me to use the left endpoint. Okay, the left endpoint. So let's think about the left endpoint right here at 36 seconds, like this. Now, the area under the curve here is going to be width times height. Well, the width is 12, and the height is, what did we say it was, 20 at 12, 28. Okay, what is width times height? Well, width is time, and height is velocity. What is time times velocity? That's distance, isn't it? Distance is velocity times time. So when you're finding the area of each rectangle, you're multiplying time times velocity, which gives you distance. Usually we say D equals VT. I kind of did it backwards, okay? Usually we say D equals VT. So it's written backwards. But the list distance is velocity times time, which is your length and your width, or your width and your height of each rectangle. So it makes sense that these areas are given distance. Very logical. So let's do it. Okay. So the area under the curve, using the left endpoint, is delta x, which is consistent at 12 every time, times f of x sub 1, f of x sub 2, f of x sub 3. How many rectangles do we have? 1, 2, 3, 5. F of x sub 4, and f of x sub 5. It's amazing how simple the concept is, and yet how much information it gives us. So delta x is consistent at 12. F of x sub 1 is f of what? If you're using the left endpoint, this is f of what? 0. The next one will be f at 12. The next one will be f at 24, f at 36, and f at 48. Note, we never compute f at 60 in this case. Using the left endpoint, we don't ever compute f of 60. So you might put on here, f of 60 is not used when we use the left endpoint. We don't ever use the height at 60 seconds because we're using the height at initial point. So this becomes 12 times f of 0 from my table. The height is 30. F at 12, the height is 28. At 24, it's 25. At 36, it's 32. And at 48, it's 24. Does this turn out to be 1548 miles or feet or what? I mean, they really didn't give me a unit. But this is distance traveled in that time. Probably more like, well, feet. Okay. Did I do one of them wrong? At 36, it should be 22 right here. Okay. Thank you. There it is. 30, 28, 25, 22, and 24. You probably typed it incorrectly, even though I had it written incorrectly. Okay, so you can see just how easy this really is. Okay, it's very powerful. It really is amazing how simple the concept of being the area under the curve can give us this nice information. I didn't number this, but we could have numbered this number 1. Okay, you could have numbered, where is it? You could have numbered this like example 1 under part C, and I'm getting ready to at least set up example 2. This is from our textbook, which is example 2 on page 249. I was looking at 2 books whenever I was doing this. Let's see if this is the book. Yeah, okay. Okay, here's the example straight from our book. It says the velocity function of a projectile fired straight into the air is f of t equaling 160 minus 9.8t. Use the summation technique, summing up the areas under the curve, to estimate how far the projectile rises during the first 3 seconds. How close do the sums come to the true or exact value of 435.9 meters? So in doing this question, Okay, we can write a little of this data down. The velocity is given as f of t. Instead of giving us v of t, y'all got to be really careful. The velocity here is f of t equaling 160 minus 9.8 t, and that is the velocity. And then they want to know how high, so you throw projectile fired straight up, projectile fired straight up, how far does the projectile travel during the first 3 seconds? Actually, I better put the word first. Now, you would have the choice here to use the midpoint, to use the left endpoint, or to use the right endpoint. It'd be completely your choice, just so long as you know what you're doing, right? So in this case, you're just as with the last case, your velocity would be the height of your function. Your time would be your horizontal value. So velocity times time, which would be the area of every rectangle, would be the distance traveled. So how 3 seconds? 1, 2, 3. It's up to you to use the right endpoint or the left endpoint. 160 minus 9.8. Let's kind of jog this thing here, because at time 0 you're at a height of 160. At time 2 you're coming down. At time 3 it's still going to be up there. So let's go from 130 to 140 to 150 to 160, because at 0 you're at 160. At 1 you're at 160 minus 9.8, which is 150.2. At 2 you're at 160 minus 19.6, about 140. At 3 you're at 160 minus 24? No. Is that right? $130.6 about right here. So this is supposed to be linear, right? There you go. So now it's up to you. Do you want to use the right endpoint, the left endpoint, or the midpoint to come up with that value? And you really could, here we are figuring like crazy. The velocity at 0 is 160. Oh, which I really should have said F, right? It's so hard for me to leave that in F. The velocity at 1, the velocity at 2 seconds, and the velocity at 3 seconds. And so you could pick with those numbers whether you want to use the left endpoint or the right endpoint. And I'm going to stop right here and have all the men do the left endpoint and all the women do the right endpoint, and we'll compare. Okay? Men on the left do the left endpoint, and all the ladies in the room do the right endpoint. And we'll compare the two. Taking the average of the two would give you a very good estimate. Okay, we'll compare once you get the figures. It shouldn't take you too long. Your delta x is 1, right? So the left endpoint is what?
450.6.
Anybody get the right endpoint? I heard that!
What?
ladies are more accurate. They're more decisive.
Oh, that's
Yeah.
Oh, they're not more decisive. Actually, they take a little longer to get to the decision, but the decision is usually the best one.
I think there's a lot more work. I don't think there's a lot of decision making.
Did any of you ladies have it yet? Dun, 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 dun. How did y'all get that so fast? Because y'all already had the values or something? Okay, ladies, any of you want to say anything? They're all too shy. They're through. Yes. There you go. Many of them are looking up, but they're not as loud as you men. How's that? There we go. So really the area under the curve, the true distance is somewhere between 421 and 450. I don't know, maybe it's 430 or 445 or something. So, but you can, that's pretty amazing that you can come up with that distance. Pretty nice. Now, there's a nice statement here when you start taking the area under the curve, and I don't think they're going to really push this in homework or anything you have to do, but this is something you need to recognize, which is, again, to compare displacement to distance. Y'all remember the difference. Displacement is the difference of the location you start with and the location you end, which is fine if you're going one way. But distance is, well, what if I move forward 4 feet and then I back up 10, and then I move forward 12, and back and forth, which displacement doesn't take any of that into account. So displacement is just initial minus final location. Distance includes all the backward and forward, and so distance could be much more. Depending, if you're going backwards, your velocity is backwards. So now, if you're computing your area under the curve and your velocity becomes negative, which would be the height would be negative, which means it's under the x-axis, it would make your area values negative, right? So if you took the positives and the negatives and add them together, that would give you displacement. It might be 0. You might start at an initial point, run your errands, and come back to an initial point, which means displacement is nothing. But distance would still be there. So when you have negative velocity, your area under the curve will be under the x-axis, making it negative. So if you're having to do this and you're looking for distance traveled, you have to take the absolute value. So let me see if I can find this on page 251. This page 251. There it is, a number right there. Okay. If the object reverses direction one or more times during the trip, then we need to use the object's speed, which is the absolute value of velocity. Okay, make it positive, which is the absolute value of the velocity function, to find the total distance traveled. So if your velocity is negative and you want to find distance, you'll have to take the absolute value of the velocity so you negate your distance. Using the velocity itself gives instead an estimate of displacement. So displacement, it's fine if your velocity is negative, your area will be negative, and if you come up with a negative distance, then you're to the left of your initial point. But to find true distance, you must take the absolute value of velocity anytime it turns out to be negative. So, and here it's written again, we estimate distance traveled rather than displacement when we use the absolute value of the velocity function. The absolute value of velocity is defined as speed. The speed of the rock. It must be falling. Okay? So again, when you're looking for distance, and we haven't had this issue in any of these examples, but if you're looking for distance and if your velocity ever is negative, you must take the absolute value of velocity. So if your velocity is ever a negative value and you're looking for distance, you must take the absolute value of your velocity to get your true distance, which is called speed. So speed is the absolute value of velocity in order to get your distance. I don't think I assigned any of that in your homework, but I can't guarantee it. But if you see it, don't forget that you need to take the absolute value. Now, another concept that's in this section, which is not a difficult one, but keeping the vision in your mind of what the concept is rather than just the algebra you're involved in, is called the average value of a function. I think this is part D. The average value of a function. Now, when they talk about the average value of a function, what you need to know is that the goal here, the average value of a function, is the average height. The average height, or the average vertical value. Okay, we're not talking about area under curve, or we're talking about area, these rectangles. You're talking about what is the average height of the function, in a certain interval. Now, when you want to know the height of a function, okay, and you're still talking about, it still relates to all the area under the curve. If you have a rectangle and you want to know the height of the rectangle, which is the question, how high is it? Well, you know that area is height times width. So if you want to know height, you're going to take the area of the rectangles and divide them by the width. Okay, so don't confuse. This is a very simple concept. The area divided by the width will tell you the height, which is what you're wanting to know, the average height of all the rectangles under the curve, which is the average height of the curve itself. Now, the book does a pretty good job here of describing this, and I'll pull this up for you on page 252. Okay, there's a paragraph here that helps emphasize what I'm trying to state. Okay, right here. Well, here's a graph. Here's an awful graph, okay? What is the average height of the line during the interval of a to b? The average value of a function can geometrically be determined as the area divided by the width. So the average, how high? This is about the average height of the function in this region. How high is it? Well, why in the world would we ever want to know that? Well, over here it talks about it. This is a very good written description. What if we want to find the average value of a non-constant function? This is a non-constant function. This is a constant function. We can think of this graph as a snapshot of the height of some water as it is sloshing around in a tank between enclosed walls between A and B. So if you visualize a tank of water with a square base, and you're visualizing it, like a wave going back and forth. I visualized some stupid show I saw where there was a truck, big truck that had a tank of water, and the height of the water was relatively low, and they threw a guy in there with obstacles and said get from one end to the other while the truck was going down the road, and the waves, they had to go from one end to the other and grab a flag or something and then go back and tag it at the top of the town. I don't know, it was really interesting as the truck was going down the road. I would never want to do this, but that's kind of what comes to my mind, of this water sloshing around. And so it says the average height, what does it say? As the water moves, its height over each point changes, but its average height remains the same. When the truck stops and the water finally sits still again, you have the average height of the water over all the time it was sloshing around. To get the average height of the water, we let it settle down. Truck has to be still until the level and its height is constant. The resulting height will equal the area under the curve divided by the width. And we let this define the average value of the non-negative function over the interval, blah, blah, blah. So there is a reason to kind of want to know that. That's a very interesting show because it works beautifully with this paragraph of information. Watching that person get into that tank and then that truck take off. It was just water, but it was just an interesting, stupid, I guess, challenge. But that's it's kind of fun. Okay, so let's do an example from the book. Let's do example 4 on page 252. So again, you're looking for average height of the function by taking area divided by width. And so here it is, very quickly here on the same page. Estimate the average value, and I keep writing here average height, I can't emphasize that enough, of the function f of x equaling sine x on the interval from 0 to pi. So the function is f of x equaling sine x, and this is the last one before we'll take a break. And the width, well, is pi. The interval is from 0 to pi. So if we want to know what the average, it says the average value of the function, which again I'm going to emphasize is the average height, it will equal total area, right, divided by width. Okay. So we got to decide how we want to divide this thing up. I did it using a delta x of pi fourths. So I did it with pi fourths, then pi halves, then 3 pi halves, no, 3 pi fourths, I'm sorry, and then pi. And then if you drew the sine wave, a sine has a maximum value of 1. So at 0, your height is 0. At pi halves, your height is 1. And at pi, your height is 0 again. And at pi fourths, it's square root of 2 over 2, which is 0.7071, which would be pretty high. Say about right here. And then at 3 pi fourths, you're once again at about that height. And this looks like a point. How am I going to round this one off? Like so. Hey, I did that pretty good. Okay, so the average value is the total area divided by the width, or it's 1 over width times total area, right? I'm going to pause this recording for just a second. Okay, so let's finish this question now that we've all had a break. Okay, so the average value, the average height of the function is the total area divided by the width. Well, the total area under the curve is what we've been doing all along. So we need to find the total area and then come in here and divide it by the total width, and the total width is pi. So let's start off by getting total area. Okay, just area under the curve. Just get the area under the curve. Well, the area under the curve, we got to decide. Y'all want to do right endpoints or left endpoints, or what did I do? I think I did the right endpoint. Yeah, I did the right. Okay, so if I do the right endpoint, then it's delta x times f of pi fourths, f of pi halves, f of 3 pi fourths, and f of pi. That's the right endpoint. So I never did f of 0 because I'm using the right endpoint. Well, delta x, we've chosen a width of pi fourths. F of pi fourths is this height. Well, what is the function? The function is sine x. Okay, so sine of pi fourths is square root of 2 over 2. Sine of pi halves is 1. Sine of 3 pi fourths is square root of 2 over 2. And sine of pi is 0. So this is pi fourths times 1 plus the square root of 2, which is approximately 1.8961. Okay, now you know this is not your answer, because if this is the sine wave, the maximum height it ever gets to be is 1. So your average height has to be less than 1, right? Because the maximum height is 1 of this function, so the average of all the heights has to be a lot smaller than that. So to get the average value, the average height of the function, we now take the total area divided by the total width. Okay, and the total area is 1.8961, and the total width is pi. And when you do that, you get a 0.6036. Well, it should be pretty good. You know, if this is 0.7 and this is 1, 0.6 would be, you know, just about in that region, which should level out in that region. So we should be pretty close. Pretty close. And what I'm visualizing is if this is a, what do we get, 0.6? Be probably about right in here. Okay, so if you took this region, cut it off and tried to sit it in here, and this region, cut it off and sit it in here, then you're pretty close. Okay, if you kind of cut it into pieces to see if you come up with that average height at about a 0.6, then we should be on track. Okay, pretty good idea. Okay, so that is the end of section 5.1, which was talking about finite sums. Really, we're talking about the area of a finite number of rectangles under the curve. And eventually this will grow into integration, but not yet. Okay, so let me close this recording.